Hello students, welcome you all. Now in NMR spectroscopy, today I will explain the general instrumentation diagram for NMR spectrophotometer. And we will see two types of spectrophotometer. One is continuous wave NMR and second one is Fourier transform NMR spectrophotometer. Now in instrumentation, actually these two types of spectrophotometer can be used, where one is when frequency is varied and magnetic field is kept constant, and another one is when frequency is kept constant and magnetic field is varied. So second one is the most common, where frequency is kept constant and magnetic field is kept changing. Now, if you will see the general flow diagram for this NMR spectrophotometer, then it is like this. So first of all, in NMR spectrophotometer, we have a strong magnet. These are the strong magnet having this north pole, and suppose this is south pole. And between this strong magnet, a glass tube or sample holder is kept. So suppose this is our sample holder in which a sample is present. This is the sample holder. Okay, so this is our sample holder, or it is made up of a glass tube, and actually this is 5 mm diameter. This glass tube is of 5 mm diameter, and here we can fill around 0.4 ml sample can be filled in it. Now this glass tube or this sample holder, this is kept rotating. Actually, it is continuously rotating in between this strong magnet. And now, so this is surrounded by the coils. So suppose this is the coils, and suppose this is our detector, RF detector, and here we have a radio frequency source, that is RF source. Now, so these strong magnets, they are also surrounded by the sweep coils. They are surrounded by sweep coils, and this is our sweep generator. In the same way, this south pole magnet, this is also surrounded by a sweep coil, or we can say electromagnet coil. And finally, we have a recorder over here. So in between this detector and recorder, we may also have the amplifier also. So this is the simple flow diagram This is a simple flow diagram for NMR spectrophotometer. Now, so as I told you, so this is a sample holder which is made up of a glass tube. The diameter of glass tube is 5 mm and it can have a 0.4 ml sample is filled in it. And now, so this is a strong magnet, as we know that we take the NMR spectra in presence of a strong magnetic field, and we have a radio frequency source also. So in presence of this radio frequency source and this strong magnetic field, the nuclei which are present in the sample is present here, the nuclei present in the sample, it starts to precess, and when the precessional frequency of the nuclei in the sample, when it becomes equal to the frequency of radio waves, then the resonance takes place and the nuclei will get excited from its alpha state to the beta state, and when it returns back to its lower energy state, then emission of energy takes place, and we get, during emission we get a NMR signal, and here we get a NMR spectrum in a recorder. So here we can, what I told you, that usually in NMR spectrophotometer the frequency is kept constant. So this radio frequency, this is kept constant, and the magnetic field is varied using the sweep generator. This is also called as the sweep coil. These are called as the sweep coil, and we have this sweep generator. So with the help of this sweep generator, the magnetic field is varied. Field is varied. So when this magnetic field is varied, then every type of proton, so magnetic field is varied from lower to higher value, then each type of proton in a molecule that can be scanned one by one. So this is about the simple flow diagram for NMR spectrophotometer. Now let us now discuss the difference between two types of spectrophotometer. One is continuous wave and another is the Fourier transform NMR. So let us differentiate these two types of NMR. So one is continuous wave and another is FT NMR, and this is continuous wave NMR. One thing that this continuous wave NMR, this is a old method, and this is a modern method of determination. Now, so in the CWNMR, as I told, the two-way, we may have two types of instrument. In one way, that is, in one, the operating frequency, new operating, is changing, is varied, and magnetic field is constant. Or otherwise, the magnetic field is varied and the frequency, operating frequency, is kept constant. So what I told you, so this is the common type. This is usually it is used. So this is a most common type of NMR spectrophotometer. Now in FT-NMR, the nuclei here, they are bombarded with high frequency pulse. So nuclei here are bombarded with high frequency or high energy, we can say, or high frequency suppose it is 90 megahertz high frequency pulse. Okay, so pulse, that is the high frequency radiation is bombarded. Pulse is a high frequency radiation which is bombarded for a very short interval of time. So this is high frequency radiation. Pulse is a high frequency radiation for a short interval of time. For short interval of time. So this is called as a pulse. Usually for 1 to 2 seconds it is bombarded. Okay, and we can represent the pulse. The pulse is represented in this way. This is the pulse. So as we can see, this is only a very small time. This is the time. For a very small time it is bombarded. Means first it is, suppose the source is on for only 1 to 2 seconds and very soon it is off. And this intensity of pulse, so this shows the intensity of pulse. This shows the intensity of pulse. So high frequency pulse for a short interval of time, or otherwise high frequency, that is 90 megahertz suppose. So 90 megahertz doesn't mean that it contains only a frequency of 90 megahertz. No. So the range, it covers complete range from 1 to 90 megahertz. So we can also represent the pulse. We may also represent the pulse in this way. We may represent. So here it shows the complete range of frequency. This is a frequency, and here complete range of frequency is shown. Complete range of frequency. It covers the complete range of frequency. That is called as the pulse. Okay, so it is a high frequency, means high frequency pulse, and it is the covers from here to here, means suppose from 1 to 90 megahertz it covers. It doesn't mean only it has the frequency of 90 megahertz. So that's why as it contains the very high frequency pulse, so all the protons, that's why all the protons in a sample, in a molecule, is scanned simultaneously, because it is so much high frequency that all protons are scanned simultaneously. This is a very important point. All protons in a molecule are scanned simultaneously in a one time. Okay, so but here, as frequency is varied, here magnetic field is varied. Frequency is kept constant, magnetic field is varied. So each type of proton here is scanned. Each type of proton is scanned one by one. Okay, so it is not all here. Simultaneous scanning is not there. So here each type of proton in a molecule is scanned, or we may say that, or excited Each type of proton in a molecule is scanned or excited one by one. One by one. That is what we can say. The most de-shielded proton is scanned first. That is the proton which is surrounded by the electron. We know that protons are surrounded by the electron. So if protons are surrounded by less number of electrons, then it is called as a de-shielded proton. And if protons are surrounded by more number of electrons, then it is called as a quite shielded one. Okay, so it depends upon the surrounding electron. If surrounding electrons are more, then it is called as the shielded one or highly shielded. If surrounding electrons are less, then it is called as the less shielded. So here the shielded, de-shielded proton, which are surrounded by less number of electrons, are scanned first, okay, at lower magnetic field, and shielded proton are scanned later at higher magnetic field. So that is the shielded, de-shielded proton. Here the de-shielded proton are scanned first at lower magnetic field. Magnetic field, because magnetic field is varied from lower to higher. So at lower magnetic field first, the de-shielded proton are scanned, whereas shielded proton are scanned later. At higher magnetic field. Okay, so this is the difference. So here what I told, all protons are scanned simultaneously at a same time, at a time, we can say at a time. Okay, so here all protons are scanned one by one. So since all protons are scanned at a time, so this is the time domain signal is obtained here. This is time domain signal. We say that time domain signal is obtained in FT-NMR. Whereas in CW-NMR, we get a what type of signal? Frequency domain signal is obtained. Okay, so frequency domain signal is obtained. And another one very important thing, that here the scan time is very less, because all protons are scanned simultaneously. That's why the scan time is very less. Scan time is very less. So then the relaxation time. So as all protons are scanned simultaneously, that's first scanning is complete, then relaxation occurs. So scan time is less than the relaxation time. Okay, so that's why we get a so all protons are scanned simultaneously, because scan time is very less. So now here the scan time is more, because the protons are scanned one by one. So here scan time is more than the relaxation time. So as scan time is more, means spectrophotometer take a lot of time to scan, and between that time, between that time the relaxation of the nuclei from beta state to alpha state cannot take place. Okay, so scanning is time of scanning is very large, so in between that time relaxation cannot occur. So that's why in the spectrum we can observe a noise also. So with a signal, the noise also appear in a spectrum. So if you will see the spectrum, then the signal appears with the noise. So this is the suppose signal, and with signal we will also observe some noise also like this. We will also observe the noise. So this is called as the noise. So if you see, then this is our main signal. So this is the main signal, whereas this part this is called as the noise. So in my previous lecture, when I discussed the sensitivity, then I discussed about the signal and noise ratio, and what I told you, when signal by noise ratio for any instrument, that should be high. So if signal by noise ratio is high, then sensitivity is high, and in that case we get a good intensity signal. So here, so if you will see, then signal and noise ratio is very less. So if you will see the signal and noise ratio, so the noise are touching the signal also, so that's why signal and noise ratio is not very high, it is quite low. So that's why so this ringing, so this is the ring, this is called as either noise, or we can say this is ringing, it is also called as the ringing, noise or ringing. Okay, so here, as I told, the spectrophotometer starts to scan the proton one by one. Okay, so it means the pen moves from left to right, where you can see the pen moves from left to right. It means from this de-shielded side to the, from lower magnetic field side to the higher magnetic field side, or from de-shielded side to the shielded side. So in my next lecture I will also discuss about the shielding and de-shielding in detail. Okay, so in this way, so that here we will not observe such type of noise. So here we are getting the noise. So noise is appeared in a signal, in a spectrum. Noise appears in the spectrum. Here we will not find no noise appear in a signal, appear in a spectra. So these are the few differences. Now other differences, some more important differences, if you will see, then let us see some more differences. Now suppose if we have one of the molecule, phenylpropanone, suppose if we have a phenylpropanone, this is our phenylpropanone, and in phenylpropanone actually we have a three type of proton. One is the CH3 proton. These three proton, the three proton of this CH3, they are in same environment. Another type of proton is CH2 proton. Here two protons of this two CH2 protons are having the same environment, and here the 5 phenyl proton are having the same environment. So 3 type of proton are there. One is the CH3 proton, another is the CH2 proton, and all these 5 phenyl protons are present. Now in CW NMR spectra, we will get the this is signal. 3 signals would be there, and the signal also contains some noise also. So at baseline some noise will also be there with the signal. But in FT-NMR spectra, as all the protons, all these 3 type of proton, all 3 type of proton are scanned simultaneously. Okay, so or we can say all the 3 type of proton are excited simultaneously, and they also relaxes simultaneously. They decay, the decay of all the proton also takes place simultaneously, and that is called as the free induction decay. So in FT-NMR, as all protons are excited and relaxes simultaneously, or we can say or they decay simultaneously. Relaxes means we can say or decay simultaneously. So this process is called as the free induction decay. So this is called, this type of decay is called as free induction decay. So as all the protons are relaxing simultaneously, so that's why all the 3 frequency, all these 3 type of proton, they will resonate at 3 different type of frequency. All these 3 type of proton, it means they will give 3 signals, or we can say they will excited at 3 different frequency, and they will also emit 3 different frequency simultaneously. So or we can say that all proton emit different frequency here this molecule will emit 3 different type of frequencies. Suppose 4 type of protons are there, then 4 different type of frequencies emitted. Here 3 type of proton is there, so all 3 protons emit different frequency. Okay, all 3 protons will emit different frequency at a time to give a complex superimposed spectra. So here we will get a complex spectra. Why? Because all 3 type of frequency, they are emitted simultaneously, and that's why they will superimpose with each other. Now suppose we get 3 different frequency. One is due to this, another is due to this, and next one is due to this 5 proton. So suppose due to this 5 proton, the frequency which is emitted, the emitted frequency is something, suppose like this, it is emitted. Now suppose due to this frequency which is emitted, is something like this. Now frequency, this which is emitted due to this photon, it is something like this. These are the oscillating frequency. So as all these three frequencies are emitted simultaneously, that's why they will superimpose to give a complex spectra. So they will superimpose to give a complex time domain signal. Time domain signal, because in a single time, at a time, all three are excited and relaxing. So that's why a time domain, a complex superimposed signal is obtained. So we will get a signal something like this. We will get a signal. We can represent it in this way. So I can represent superimposed, these three frequency get superimposed, and we may represent like this. So this is a complex signal, and this is a time domain signal. This is a time, and a complex time domain signal is obtained. Now this complex signal, which is a time domain signal, this is converted into the frequency domain signal. Now this would be converted into frequency domain signal. This is now converted into frequency domain signal. How it is converted? So this time domain signal, this is converted into frequency domain signal with the help of a software, mathematical software, which is called as the Fourier transform. So this converted into frequency domain signal by a mathematical software, called Fourier transform. Fourier transform software will transform the time domain signal into the frequency domain signal. So now after conversion, so here all the frequencies are overlapped with each other. Now after that, the frequency will separate out. So after the frequency will separate out, and we will get the something signal like this. We will get a separate signal due to these three different kind of photon. We will get a signal like this. So one signal is like this, another is suppose like this, next one is like this. So these three signals are obtained. Suppose this is for TMS, that I will explain in my next lecture what is this TMS. So three different signals. So suppose this is for 5, this signal is for 5 phenyl proton. So this 5 phenyl proton is giving one singlet. Here this 2 CH2 proton is giving one singlet, and here suppose 3 methyl proton is giving one singlet. So in this way, this overlapped signal is converted into the separate signal, and here we get the we are getting not in terms of frequency, we are getting this signal in terms of chemical shift, that is represented in delta, that is in ppm. So this is called as the chemical shift. And to convert the frequency, suppose this frequency, it may resonate at 10 hertz, this resonate at 8 hertz, this resonate at 4 hertz, so like this. So this frequency is then converted into the delta value. This frequency is converted into delta value by the formula we know. This chemical shift, I will discuss in my other lecture about this chemical shift. So this can be converted, the frequency of the signal can be converted into this delta value by this chemical shift formula. This chemical shift, that is delta, this is equal to frequency of signal in hertz. This is the frequency of signal in hertz divided by spectrophotometer frequency in megahertz multiply by 10 to the power 6. So by using this formula, we can convert these frequencies, different frequencies, that can be converted into the chemical shift delta value by using this formula. So this is the frequency of proton in hertz divided by frequency of spectrophotometer in megahertz multiplied by 10 to the power 6. So here, such type of spectra is obtained, whereas in CW-NMR we get this type of spectra, same spectra is obtained, but some ringing or noise may be there. So in this spectra, various noise will be there at this baseline. So this is called as a baseline. This baseline is not so clear in this CW-NMR. Here, lot of noise would be there at the baseline, whereas in FT-NMR, no baseline is there. So these are the some differences. Now let us see some advantages and disadvantages. So what are the disadvantages of CW-NMR and what are the advantage of this FT-NMR? Let us see. So CW-NMR, it has certain disadvantage, whereas this FT-NMR, it has lot of advantages. Now, one of this FT-NMR spectra, so this requires the sample requirement is very less here. So here one thing or another, like we saw here, the noise is very less. Noise is very less. Very less. Here noise is more. Okay. Now next one, so this FT-NMR, the sensitivity of this instrument is very high. Okay, so here the sensitivity is low. Is low. So as sensitivity of this instrument is very high, that's why we can also analyze the low abundant nuclei also. So it can analyze low abundant nuclei also. For example, C13 nuclei can easily be examined here. So it can only analyze high abundant nuclei. For example, this we know that this proton, the natural abundance for proton is above 98%, 99%. So, or next one, here as sensitivity is very high, so the sample requirement is very less. sample requirement is very less. Here the sample requirement is more. It requires large amount of sample. So next one, the time required for, as I told, the time required for to analyze the sample is very less. Time required is very less. Here it require more time to analyze the sample. Than FT NMR. So these are few differences between the continuous wave NMR and FT NMR. Hope you are understood. Thank you.